All right, let's get right into it. Today, we're talking about a machine that is, quite literally, the heart of so many industries, the centrifugal pump. Now, whether you're a new engineer on site, a hands-on technician, or even prepping for that big job interview, really getting these machines is a skill that'll define your career. So, let's get started. So, what you're looking at here is the complete hydraulic path of a standard centrifugal pump system. You got your tank, the suction line, the pump itself, and the discharge line. Looks clean, simple, right? Almost like a textbook diagram. But I'll tell you what, the gap between this neat little drawing and a machine that runs reliably for years, that's where the real engineering happens.
So the real question is, are you ready to bridge that gap? Because that's exactly what we're going to do. We're going to go from the theory on the page to the practical skills you need on the project site. Let's do this.
Look, every great pump system starts with getting the numbers right. Before you even think about ordering a single piece of pipe or turning a single bolt, you have to nail down the fundamental physics. This is the bedrock of your entire design.
First up, total dynamic head, or TDH. Just think of it like this. TDH is the total amount of fight the system is putting up against your pump. It's how high you have to lift the water, plus all the friction from the water rubbing against the pipes and fittings. And you have to get this number right. If you calculate it too low, your pump's just not going to have the muscle to do the job. If you calculate it too high, you've just wasted a ton of money on an oversized pump that's going to gobble up electricity for its entire life. Getting this number wrong is like buttoning your shirt wrong. Everything that follows is going to be off.
So, once your pump is pushing against that TDH, how much good is it actually doing? Well, that's what we call hydraulic power. This is the payoff. This is the useful work, the reason you bought the pump in the first place. It's a direct measure of the flow and pressure you're actually creating. This is the output you care about. But here's the thing. The work you get and the power you need are two different things. Brake power is what the motor actually has to spin with. It's always going to be higher than the hydraulic power. Because, well, no machine is perfect. There are always losses. So, why is this so important? Because this is the number that shows up on your electricity bill. This is the power you pay for.
And that brings us to the magic number that connects the two: efficiency. It's a super simple ratio, the useful power you get out, divided by the total power you had to put in. A pump with high efficiency is just a money-saving machine. It's better at turning that electricity you're paying for into the water movement you actually need. This number tells you how good your pump is at its job.
Okay, we've done the math. Now, let's get our hands dirty and move to the project site. And I'm going to say something here that might sound a little crazy. A perfect installation of a decent pump is way, way better than a terrible installation of a top-of-the-line pump. This is where most failures are born, right here.
So here are the steps you just can't skip. You need a solid concrete foundation to soak up vibration, otherwise the machine will literally shake itself to death. Then you need laser-precise alignment between the motor and the pump. We're talking fractions of a millimeter here to save your bearings. And that suction piping, it is the single most critical piece to get right. After that, you connect everything up and do your tests. Rushing any of this is basically asking for a breakdown in a few months.
Let's look at the classic mistakes I see all the time. Slapping an elbow right onto the pump suction, you're sending choppy, turbulent water that hammers the impeller. Using the wrong kind of reducer, you're basically creating a little bubble trap for air that can starve the pump. And putting a flexible joint on the suction side, it can actually collapse on itself. These aren't just details, folks. These are the direct causes of catastrophic failure.
So, how do we guarantee those expensive mistakes don't happen? Before you ever hand over the keys, that system has to pass a tough quality control check, an inspection and test plan. This is your proof. You're double-checking the alignment, pressure testing the pipes, making sure the motor's good, and then you run the whole thing to measure its real-world performance. This is your final stamp of approval that the job was done right.
Okay, the pump is installed and checked out. Now, how do we run it smartly so it has a long, happy life? There are two concepts every single operator and maintenance tech has to live and breathe to prevent the absolute worst kinds of failures.
First one is net positive suction head, or NPSH. It sounds complicated, but the idea is simple. You need to have enough pressure at the pump's inlet to stop the water from boiling. Yes, boiling. If the pressure drops too low, tiny vapor bubbles form and then collapse with incredible violence inside the pump. That's called cavitation. It sounds like you're pumping a bunch of rocks because it's literally chewing your impeller to pieces. The key thing to remember is there are two values: NPSH available, which is what your system gives the pump, and NPSH required, which is what the pump needs. Your one job is to make sure available is always, always bigger than required.
The second big concept, especially if you have a variable speed drive, is the affinity laws. And this chart just says it all. Check this out. You bump up the speed by a little 10%, you get 10% more flow. That makes sense. But look at the power. It doesn't go up by 10%. It shoots up by 33%. That's because power is related to the cube of the speed change. Understanding this is absolutely critical for saving energy and making sure you don't burn out your motor.
So you learn all this stuff. How does it actually help you in your career? Simple. It makes you credible. It makes you valuable. It makes you the person they want to hire. Knowing the why behind all the rules and formulas is what separates a good technician from a great one.
Real professionals don't guess. They follow standards. These documents, whether it's NFPA for fire pumps or API for oil and gas, are basically the collected wisdom of the entire industry. They are rulebooks written from decades of learning from other people's mistakes. Designing without them isn't just unprofessional, it's flat-out dangerous. Knowing which standard applies to your job is always step one.
All right, pop quiz. You're in that job interview. The manager leans forward and asks, how do you prevent cavitation? A great answer isn't just give it more pressure. A great answer is, I ensure the net positive suction head available from the system is always greater than the NPSH required by the pump. I can do that by raising the suction tank or by designing the suction piping to be larger and shorter to minimize friction loss. See the difference?
Then they hit you with the follow-up. Okay, what happens when you change the pump speed? Now you can confidently explain the affinity laws. You tell them flow changes 1-to-1 with speed, but head changes with the square of the speed, and, here's the kicker, power changes with the cube of the speed. That shows you understand the huge impact it has on energy and motor selection. Final interview question. What's the #1 reason you see pumps failing early on a project? It's not a bad design. It's not a faulty part from the factory. After everything we've just talked about, you know the answer. The single biggest killer of pumps is, almost every time, a bad installation.
So here's the bottom line. Knowing the formulas is great, it's important, but knowing how a machine actually fails out there in the real world, that's what makes you an expert. And now you have a solid foundation for both. You've got the design, the installation, the operation, and you know how to talk about it like a pro.